The final situation we considered is the reflection by a curved mirror. The radius of the curved mirror is R0. So here, the blue line represents the curved mirror with the radius is R0. And due to this mirror is a perfect mirror, the amplitude after the reflection will have no change. So the curved mirror will only provide us the phase variation after reflection. And what will be the phase changed after the reflection by the curved mirror? Let's see. We consider a plane wave shown here with the green line. The green dashed line stands for the phase front of the plane wave. As the plane wave goes this way, and the point here hit the mirror. As the phase front hit the mirror, you know that the point here will then go backward, but the center point will still go in this way. Okay, and suppose this distance is delta L, and as the center point hit the mirror and they start to go backward, and at the same time the reflected point have arrived here. What will be this distance? Sorry, let me plot it in red line. And clearly, the distance here should also be delta L, right? Because the center point propagates delta L distance and start to go backward, and this point has propagated with the same velocity. So the distance here is also delta L. As you see, as the center point start to go backward, the point here has the distance between with respect to the center point is 2 delta L. That is why after hitting the curved mirror, the plane wave will become a curved phase front. Okay? And what will be the value of delta L? The delta L can be expressed in this way. Okay, so as I have told you, the total phase difference with respect to the center point for the point at here can be written in this way. Exponential plus j k times the optical path difference 2 delta L. And due to this point is in advance with respect to the center one, so here the phase difference is phase advanced. And take the expression of delta L into here, the phase difference with respect to the center point can be written like this. So this term represents the phase contribution by the curved mirror after reflection. According to this phase contribution, let's see. For Gaussian beam reflected by this curved mirror, after the reflection, the phase turn can also be written in this way. The phase from curvature, the radius of the phase from will become r prime. And of course, r prime, the phase turn here is the original one. Times the contribution by the curved mirror, that is this term. So, based on the phase turn shown here, we can have the conclusion that the inverse of r prime will be equal to the inverse of r minus 2 over r0. R0 is the radius of the curved mirror. And due to this relationship, we can obtain the Q transformation for the reflection by a curved mirror. That is this one. Okay, so this equation describes the Q transformation for the reflection by a curved mirror of radius r0. And if you remember in previous slide, we have derived the Q transform for propagation passing through a thin length. So for a thin length, the Q transform is written like this. And compare with these two, we can say that a curved mirror with radius r0, it can be considered as a thin length of focal distance f defined as half r0. Okay, what I am saying here is that the function of a curved mirror, just like a thin length, with the focal distance defined as r0 over 2. So you don't have to remember the Q transformation of the curved mirror. You just have to keep in mind the Q transformation of a thin length. But if you consider a curved mirror, the f here should be replaced by r0 over 2 for a curved mirror. Okay?